For our first talk today, we have Steve Flammia, who is normally at Sydney, but is currently at sabbatical at where, MIT?
Yeah,
Boston.
MIT.
At MIT. And what are you going to talk about?
Yeah, I should probably plug in my thing.
Well, you'll see what he's going to talk about.
Thanks, Daniel. I guess, can I just use this mic, or do I need the roving mic? Sorry, just give me a sec while I plug in. You want to grab that? Wait. Oh, yeah, okay. Okay, thanks, Daniel, for the introduction. It's a real pleasure to be here. I was super impressed with the list of speakers, and I was also really thrilled that there's a bunch of experimentalists that are going to be speaking this year. So I've tried to make my talk slightly more experimentalist friendly, meaning I don't have long slides dwelling on like the definition of the diamond norm and things like that. So if you're one of the theorists in the audience that was looking forward to such a thing, I regret to inform you, you won't be seeing that, but hopefully experimentalist colleagues will get a little more out of this talk as a result. So as the first speaker, I had to put up a slide like this one, which basically just says something that probably everyone in this audience already knows, that there's lots of different architectures out there for quantum computation that has shown, you know, the field has grown tremendously. There's been enormous progress among all of these and probably more. Superconducting quantum qubits, ion traps, including, I had to put a Maryland slide up because of our hosts here, spins in silicon, many, many others, Majorana fermions. And so one of the questions I want to ask is how should we count success when we're manipulating qubits? This is one of the first things that I want to touch on, which is I think an important question that sometimes gets overlooked in this quantum error correction community. So what does it mean to talk about a successful quantum error correction? And so in order to motivate that a bit, let me just review the nature of errors and noise and how we deal with them in this field. So we have two main tools that we use to defeat errors in quantum computing that demonstrate conclusively that quantum computing is not, you know, just analog computing. And the first is error correction. So we can add redundancy by, for example, this is the bit flip code. We can encode into a 2-qubit subspace in such a way that if we measure, for example, the joint parity, the parity of pairs of qubits, we learn nothing about the state, but we learn something about the errors. And we can use this to do quantum error correction. Indeed, that's the name of this conference. And the other key idea is fault tolerance, which is the idea that if our hardware itself is faulty, and in the course of measuring those parity checks or doing other, like for example, encoded gates, if the hardware itself is noisy, we don't want those errors to spread throughout the computation. So we have to design circuits that mitigate the spread of the inevitable errors that we introduce when we interact with a quantum error correcting code or a quantum system in a noisy or imperfect way. So what's the threshold theorem? So the threshold theorem, the reason for this weird cube of color code here is because this just simply demonstrates that people have thought really hard and gotten really, really creative about ways to address the question of fault tolerance, right? So if you don't know what this means, I'm sure somebody at this conference is going to talk about it. The point of this is that people have thought really hard and gotten really creative. So the basic idea of the threshold theorem is that there are two conditions which are necessary, which are sufficient and also in some sense necessary in order to have an arbitrarily long quantum computation. So the slightly more precise statement is that if we want to do an arbitrarily long quantum computation with an arbitrarily high success probability, then we can do that as long as two conditions are met. The first is that the error rates should be sufficiently small on the individual components. And the second is that the correlations between the errors should be sufficiently weak. Okay, so I say that these are sufficient. That's what these papers show. But they're also in some sense necessary, which you can see through the following simple thought experiments. If the error rates are as high as, for example, 50%, then of course you're never going to get anything but noise out of your quantum device. And if the correlations are such that with probability p, an asteroid flies in from outer space and hits your quantum device and destroys your entire lab, well, then you'll never be able to compute for much longer than about 1 over p. Okay? So those two extremes show that we need both low error rates and weak correlations if we want to have arbitrarily long, arbitrarily accurate quantum computations. So that's the threshold theorem in a nutshell. And the best possible threshold, if we ignore other constraints such as overhead, which I'm not really going to talk about here, but I'm sure other people will address the idea of overhead. The best possible threshold is certainly greater than 0.1% error under certain specific, pretty general noise models. And it's also almost certainly less than 25% by a no cloning argument. And it's probably in excess of 1%, although there the evidence is a little more mixed because it relies on certain specific numerical assumptions or certain specific noise assumptions that are testable only really numerically. Okay, so when we talk about thresholds, we always talk about, we have to define a threshold relative to a few specific points. One being a protocol for how we choose to correct the errors, so in particular an error correcting code, as well as circuits for how we measure and extract syndromes and things like this, and how we perform encoded operations. And also then it will also depend on the noise model that we consider. So popular choices are, for example, Pauli noise models, but real noise models have a lot of non-Pauli noise like amplitude damping or coherent errors, which I'll talk a lot about. And the other thing that it depends on is the level of rigor in this specific result. So there are mathematical results that are 100% rigorous that prove a threshold theorem, and they tend to be for rather pessimistic noise models. And then there's also numerical analysis, which inevitably, almost inevitably, relies on Pauli channels or Pauli noise models. And that's just because we look for our keys where the lamppost shines light, right? We know how to do those simulations, so those are the things where we have a lot of numerical evidence. But it's unclear how optimistic those noise models might be compared to realistic noise. So the threshold provides a natural benchmark. Once I fix a few of these variables and I define a threshold, I'm saying in quotes, then that specific threshold provides a benchmark for comparing different experimental implementations. But there's one thing here that I want to address, which is what do we mean by percentage error, okay? So in order to explore this question, I'm going to look at a couple different natural noise models that I can think of as two limiting cases of natural sources of physical noise. The first one is just a pure dephasing channel. So with probability 1 minus p, nothing happens to the state, and with probability p, a bit flip occurs, okay? So this is like a high frequency limit of a dephasing process that shrinks the Bloch sphere around the equatorial directions. The other noise process is I can think of as the limit of a very low frequency noise process. So this would be like a DC static error or a calibration error. But it's also a good approximate noise model for general sources of low frequency noise. And that's a unitary over or under rotation noise. And so here I just apply with some small angle delta, I do a rotation about the z-axis on my qubit. So here, in the first case of dephasing noise, there's a very clear notion of what I mean by percentage error. It's given by p, the probability that this flip occurred. Indeed, this is a stochastic channel, meaning it makes sense for me to talk about a stochastic process whereby one of these two processes genuinely happens. But down here, there's no such interpretation. So what does it mean to say percentage error down here? So we need to talk about error metrics in order to quantify this question. And a popular one is the average fidelity, or the related quantity, which I'll define on the next slide, is 1 minus the average fidelity, which is called the average error rate. So this is a really natural quantity. It's just I apply the noise channel to some input pure state, and then I look at the echo. So I'm going to undo the quantum gate, some ideal quantum gate that I was trying to do, and I'm going to look at the residual. And then this quantity here, see I sandwich it by psi on both sides. This is now a probability. This is the Born rule probability that this echo experiment brings me back to the correct state. So I measure that probability, and then I average that probability over all pure input states. This is a very natural measure. It's one that anybody would write down. So this is going to be one measure, and also 1 minus this is the average error rate is another, they're synonymous. Or they're interconvertible, so they're basically the same. And the other one, which I won't define precisely to spare my experimentalist colleagues, is called the diamond norm or diamond distance, or sometimes called the worst case error probability. Mathematicians will call this the completely bounded norm, or completely bounded one norm. And all it is it's the interpretation of the worst case probability if I do two things. I have to take a state and I have to add correlations with some purifying system. And then I need to do a worst case measurement to try to distinguish this state from the ideal, this gate from the ideal gate that I was trying to perform, okay? So this is actually a pretty natural experiment because it embeds the correlations of the state with some environment, and you want to be describing correlations inside of a noisy quantum device, so it's natural to include this purifying system. So this is called I'll sometimes say diamond norm or diamond distance. Okay, so what's the distinction between these various errors? Error metrics. So for dephasing, if I compute this average error rate, which is 1 minus the average fidelity, I get 2/3 p. So this percentage error that we described and this average error rate, there's basically no distinction. There's a small constant factor that lets me interconvert between these two things. The other is if I compute the diamond norm distance, for this particular channel from the ideal channel, which would be the identity in this case, I get p. So there's a small constant factor difference between these two things. And so for dephasing, the distinction between average error rate and diamond norm distance and percentage error, all of these things, they basically map onto the same concept. They're conceptually interchangeable. But now when I have unitary errors, this is no longer the case. So now I apply a small calibration error to my qubit, or a small over or under rotation error. And I see that the average fidelity, or the average error rate, scales like delta squared. It scales like the angle squared. Whereas the diamond norm distance is linear in this angle, or the absolute value of this angle. So this is a key example. So these two limiting cases, these are very trivial toy models, but they capture the essential idea here, show that these two error measures are actually dramatically different. And what's more, so I referred to this, I referred to the average error rate as a metric, and that's actually erroneous for the following reason. If I add up a sequence of these gates, then they add up superlinearly. Okay, so the average error rate for a sequence of n of these coherent over or under rotations, then those rotations add up linearly, and the average error rate increases like n squared times delta squared. So it's adding up super linearly, which is a very strange and non-intuitive behavior, right? When we think about distance, we don't think about distances adding up quadratically. So indeed, it's not a metric. The diamond norm distance, however, it is in fact a metric, and it adds linearly as you would expect in this error model. So the more pessimistic error measure actually behaves more intuitively and naturally when the errors are compounded. So the diamond distance, the reason that theorists love this is because it has a bunch of mathematical properties that match exactly what we expect when we intuitively think of a distance measure. So for example, it obeys this composition inequality. So if I compose two noisy gates, then the diamond distance is at most additive. And we saw that the average error rate fails this condition. The average error rate also fails this other condition, although not by much. You can ask me about that during a break. If I tensor on an identity system, so if there exists some perfectly isolated quantum system somewhere else in the solar system, the existence of that extra system shouldn't matter to whether or not my quantum computer functions, right? So that means that if I have a noisy process and I tensor on an ideal identity gate, I should get back the same answer, and the diamond distance satisfies this. So these properties of error metrics are used in the current proofs of the fault tolerance threshold theorem, and they're also very natural things that you want from an error metric. However, the average error rate does have some nice properties. It has the property that we can measure it. So that's a pretty important thing if you actually want to build a quantum device. So in particular, there's this method of what's called randomized benchmarking, where I do a long sequence of Clifford gates, and I measure the expected survival probability of an input state after doing some long sequence of Clifford gates and then inverting that sequence. If I do this many times, then you can provably derive an exponential fidelity decay curve. And if you fit that, the slope of this lets you back out R, the average error rate, to a very high accuracy. So although this thing sort of fails in a few very natural senses to be a good intuitive measure, it's really important that we can actually measure it. So that's a very useful quantity. So one thing we'd like to be able to do is interconvert between these two things, the thing we can measure and the thing that lets us actually gain a deep understanding about fault tolerance thresholds. Unfortunately, this is hard to do using only R. So the best known general error bounds that we have that relate R, the average error rate, to D, the diamond distance, scale as follows. There's some small constant factors, D plus 1 over D, which we should basically ignore. But D can be as small as linear in R, or it can be as large as the square root of R. Okay, and there are some experiments. I mean, for example, there's an ion trap experiment where they measured an error rate of 10 to the minus 6 on their single qubit gates. So if you take the square root of that, you're talking about a factor of 1,000 difference when you compare your average error rate to your diamond distance. So there's a huge gap between what you can say about the diamond distance when you measure the average error rate and if you simply report average error rates. So in particular, if you're reporting fault tolerance thresholds and you're only using the average error rate to say something about that threshold, you need to think twice about that. You might be making a big mistake. So it matters a lot the nature of your noise. Now the flip side of that caveat is that this isn't necessarily always saturated, this inequality. We don't actually know the conditions for when this inequality is saturated, but I'll talk a little more about that in the next slide. So in particular, if you have unitary errors, we do know that it's at least close to saturated. Certainly this square root R behavior is indeed saturated if you have unitary over or under rotations. And in fact, it's always saturated. So for every unitary error, the diamond distance definitely scales like the square root of R. That is, we have a lower bound, not quite a matching upper bound. There's still some gaps here. But the point is that it scales always like the square root of R. So if you do have coherent errors in your system, then R is not a good proxy measure for the fault tolerance threshold. You're making some errors. In that comparison, you're making errors, I mean. However, for other types of errors, this is not true. So in this paper, we actually tried to exhaustively look at uncorrelated types of noise. So we didn't look at 2-qubit correlated types of errors, but we looked at single qubit noise sources like unitary noise, thermal relaxation, amplitude damping, things like this. And things like amplitude damping, for example, are always in this good linear scaling regime. They always scale like 3 times the average error rate. So that means that if you're reporting R and a dominant source of noise in your system is amplitude damping or thermal relaxation or things like this, then reporting this average error rate is indeed a good proxy for the diamond distance and you're on safe ground. Okay, so if you have unitary errors, all is not lost. We have methods for dealing with this. So, I mean, of course, I already talked about error correction and fault tolerance. That's ubiquitous for every type of noise. But we can also use things like echoes, composite pulses, dynamical decoupling, and things like this. So unitary errors simply signify that you need to do more characterization of your errors in order to reduce those errors and turn them into incoherent noise sources. Once you have incoherent noise sources, then you have to do some physics. The math's not going to help you. You have to track down there's some source of error somewhere, but it's due to some high frequency thing that you then just have to track down. The characterization tools that we have are not so good at helping you once you're in that regime, but at least you know that the proxy measures that you're reporting are correlating well with fault tolerance thresholds. You've extracted everything you can out of that coherence at that point. So, okay, I'm a little bit interested in understanding the performance of error correction under these various noise channels. So there's this nice paper by Ron Doherty and Mabuchi from 2002, where you can actually look at the effective error correction channel. I mean, it's a natural idea. I feed in I feed in a state over here, I do some unitary encoding map, I apply the noise across all n encoded qubits, and then I decode, and I look at the output state. And if it's a k qubit code, this is an effective channel on k qubits, and they discuss in their paper a natural procedure for writing down the effective error channel from k qubits to k qubits without having to understand much about, well, you can derive that effective channel from studying the noise channel acting on each of the individual n qubit channels. So you can just derive these effective Krauss operators. And then by iterating this, you can look at dynamical maps and look at fixed points and things like this, and boundaries between fixed point phases. So, okay, so we did this for a couple channels, natural channels. So we were interested in particular in these unitary channels, because these are the bugbears. They're the ones that are kind of the most annoying, and we want to understand them better. So for this unitary error, the effective channel, you can simply write it down, and you get, oh, sorry, I should say we considered a slightly more general channel actually than just the unitary channels. We included both of these two toy model channels. So these unitary over and under rotations, as well as dephasing. So if you start with just a unitary error, it maps into something of this form. You get some dephasing and some unitary errors as well. Okay, so we're interested in the dynamical map that takes delta into delta prime and p prime. You can also add in dephasing at the bare level, and you can look at the dynamical maps that iterate from p and delta to p prime and delta prime, and then you can iterate that map. So we looked at this for a few different codes, but in the interest of time, I'm just going to talk about the toy case where we looked at the repetition code. This is the simplest case. We also looked at like the 5-qubit code and a surface code and the Steen code, but I won't talk about them in this talk. So the repetition code, we're interested in rotations about the z-axis and bit flips about the, and phase flips. So the repetition code that I'm considering is going to be repetition codes in X basis states. And if I have n qubits, then where n equals 2t plus 1, then it corrects t errors. I'm also going to talk about the case of where n is even at some point a little bit later. So, and there it corrects the, I mean, t would then be a half integer, and I would have to round down to talk about the number of errors that it corrects t. But t is roughly n over 2. Right, so for the dephasing error, if I measure the syndromes, the other simplification that I'm going to do in this talk is every result that I'm going to quote is going to be a result that's expanded. It's going to be Taylor expanded to lowest order in P. Our results are actually more precise than this, but this makes the formulas a lot easier to digest, and we can just look at the leading order behavior, which I think is the key message that I'm trying to get across. So if we measure the syndrome corresponding to Z errors, then the probability of an error of some weight W, scales like n choose W, because there's W sites where I can make the error, times P to the W, the error probability. It's a leading order in P. And if I measure the syndrome, so yeah, I just said that. So I measure that syndrome. After error correction, the logical qubit undergoes dephasing with some new probability, P prime, right? This is iterating this dynamical map. And I get P now scales like n minus 2W for that effective process. We can compute the expected diamond distance after error correction. And this is going to be dominated by errors of weight T plus 1, okay? So I should say this is not what people normally calculate. People normally calculate the diamond distance of the expected channel. This is calculating the expected diamond distance conditioned on the syndrome, okay? Which is, I think, the right thing to be calculating. Because indeed, you do know the syndrome after you've done error correction. So if you do this, you get some n choose t factor, which is roughly n choose n over 2. So this scales like 2 to the n over root n, this factor in front, times p to the t, or sorry, p to the t plus 1. So I can do the same thing if I consider the unitary error case. So now I have small angle rotations around the z-axis by some small angle delta. This time the errors have weight to leading order in delta, n choose W, errors of weight W scale like n choose W, delta to the 2W. Okay, so there's a doubling that happens with respect to this parameter delta. And so now when I measure the syndrome and I report back a weight W error, so after correction, the logical qubit undergoes a unitary rotation, in fact, with a modified angle. So that new angle has a sign to it, depending on the weight of the error that happened. And it has an angle delta to the n minus 2w. Okay, so you can think of this as happening, there's going to be you can think of this error correction now as being a biased random walk where the lowest error is happening with some angle, and then the next lowest error happens with the opposite sign, but reduced by a factor of delta or 2 delta, and so on. And so this leads to some asymmetries in the error correction. That's why there's residual unitary errors in this code. So here the expected diamond distance exhibits two differences from the dephasing case, which are of interest, okay, and actually show that we are going to have to worry at least a little bit about unitary errors. So I should back up and say an aside, especially because some of the originators of the theory of quantum error correction are in this room, and they can correct me if I say something wrong. I think the conventional wisdom for about 20 years has really been, well, the coherent errors aren't really going to matter. I'm not sure if the people actually believed that or if they just said, we're actually just kicking this down, we're going to kick that can down the road because kicking the can down the road. Okay, so people probably knew it was something to worry about, but they said, let's just not worry about that. And I think the opinion that I always got was that nobody worried about it and everybody said, well, you know, this square root behavior is too pessimistic. Things are going to average out. You're going to see random walk type behavior, and you won't have to worry about it. And so I think I think the point of this talk, one of the points of this talk, is that we really should dive in and study and understand coherent errors. There are now we're building techniques to do that now. Things like tensor networks, which I think some people in this talk, some people in the audience are going to speak about later in the conference. Anyway, we have tools and techniques to study coherent errors. We really should do it because they do make a difference. So what difference do they make? We can quantify it for this very simple case. So here the expected diamond distance scales like 2 to the 2t or 4 to the t times delta to the n. So here this is bigger by a factor of about square root of n. So it scales with the size of the code, this difference. It depends on the size of the code, which I think is interesting and people may not have appreciated. And it also scales like delta to the n as opposed to delta to the t. So in the interest of time, I'm going to skip this cool looking slide and just, I'll skip a couple of those slides and say that, so the point is, in this special case of the odd distance repetition code, there's some combinatorial factor that depends on the distance of the code or the size of the code, and we get the average error rate to the t plus 1. But for unitary errors, this expected diamond distance is bigger by 2 factors. I probably should have made it explicit here in this combinatorial factor, but it's bigger by a factor of square root of r because there's residual uncorrected unitary errors. And it's also bigger by a factor of the square root of the distance of the code. Okay, so this extra thing has an extra combinatorial factor in there as well from the size of the code. Okay, so I think people, I mean, I don't know that these effects had been anticipated. And, we're going to have to worry about these things and understand them if we want to actually get below the fault tolerance threshold. I'll skip that slide too. How much time do I have, Daniel? 10 minutes? Oh, okay. Well, then let me just also say, for even distance error correcting codes, this was a surprise to me. Something interesting happens and we erase this distinction between, so this code has a little bit more symmetry. And you remember how I mentioned this bias random walk idea? You can sort of cancel out some of this unitary behavior at the code level if you make an appropriate choice of code. So this is pretty interesting. So if you use an even distance repetition code, then this factor of root r, that was the distinction between these two cases before, that distinction then evaporates. Okay, so this is kind of an interesting effect that there are extra symmetries inside the codes that you can take advantage of if you want to cancel out. I mean, okay, I'm not making a profound statement because everybody knows that if you specify channels to specific noise, you can do better, right? I mean, what I think is surprising to me is that it exactly cancels this square root of r behavior. Right. So let me build on that momentum and say, you know, what can we achieve if we really tailor our codes to our noise channels? So let me switch gears a bit and talk about biased noise. So now I'm going to, instead of talking about unitary errors, I'm going to talk about Pali channels again. But this time I'm going to talk about biased Pali channels. So for a lot of error correcting, or sorry, for a lot of physical qubit choices, T2 is still a lot smaller than T1 in these systems. There are some things like, you know, since the invention of the modern transmon, that's no longer true, for example, in superconductors. Their T1 and T2 are compatible. But in other architectures, we still see really large bias in the noise. And because I want to look for my keys where the light is under the lamppost, I'm going to study Pali channels with biased noise. So the definition of a biased noise model that I'll take is a Pali channel where with probability 1 minus p an error occurs, one of the Pali errors occurs, and each one of them occurs with probability px, py, or pz. And so the total error probability p is px plus py plus pz. I'm going to define the bias to be the ratio of a z error compared to the sum of either an x or a y error. So pz over px plus py, I'm going to call eta. That's my noise bias. I'm going to look at a very popular code, the surface code. So the surface code is popular for a number of reasons. So for one thing, if you have z-bias noise, in particular if you take the limit of infinite bias, then the standard way of defining the surface code, so here's a picture of the surface code. Probably everybody here knows it, but let me just define it. If I have a lattice of qubits where the qubits sit on the edges, and I have appropriate rough boundary conditions on these edges and smooth boundary conditions on these edges, then this encodes one qubit, one logical qubit into, you know, approximately L squared physical qubits. And the parity check operators that I need to measure in order to extract the syndrome bits look like products of sigma x around each vertex, we'll call that A, and products of sigma z around each face, call that operator B. So I measure that everywhere, and then I run some decoders, which I'll talk about on the next slide, and I can extract the syndrome. And if I do that under what I'll call the error correction threshold, that is ideal measurements, I'm not considering fault tolerance or noisy hardware, then for pure Z errors, the threshold is around 10.9%, basically about 11%. So this is a pretty large number. And it also has a high fault tolerance threshold. So using these Pali noise models, which may be a bit optimistic, the threshold can be around 1%, again, if we don't worry about overhead and things like this as well. So that's a very high threshold. It's made it a very attractive architecture. Also, I alluded to this, but let me just say it explicitly. All of the stabilizers are geometrically local, right? This is why everybody is so excited about topological codes, because I can make a local layout of qubits. This is very attractive if you actually want to build one of these devices. So let me just say a bit about decoders. The other reason that the surface code is popular is that this local structure enables people to really build some physical intuition into the decoding of the syndrome information. So here are just a handful of decoders that people have studied in the literature. There's too much work on this for me to cite everybody, so I apologize if I missed your paper. Minimum weight matching is by far the most popular decoder, and here we want to find error chains. So we can observe in this surface code, we can of course observe, if I flip a bit here, we have this interpretation that we see the endpoints of an error chain. So what I want to find is the minimum spanning error chains that connect up all the errors and map you back to vacuum. There's a polynomial time algorithm for doing this. This is called the minimum weight matching decoder. And it achieves things very close to this 10.9 number that I quoted on the other page. So this is a very popular decoder and it works really well. There's a lot of modifications of this in the literature. Another popular one that people have explored because it's very flexible and it has good physical intuition is this notion of an RG decoder. RG stands for renormalization group. So the renormalization group decoder family does the following. It measures all of these syndromes and then it collects them into hierarchies based on length scales. And there's various ways to do this. You can pass information from the lower length scales up to the higher length scales using belief propagation and things like this. Or you can just use a more naive hard decision clustering algorithm as well. But the basic idea is that we're smoothing out the errors that are occurring on the smallest length scales, which physically would correspond to very high frequency things. And then we're slowly dialing that back to lower and lower frequencies. And if we flow to a fixed point of, well, we'll eventually flow to a vacuum fixed point. But if we're on one side of the error correction condition threshold, then we're flowing back to a situation where all of those errors are confined, and we don't see any strings that loop around our torus or across our surface code. And so it uses this beautiful intuition from RG about flowing towards fixed points under renormalization group transformations to define an explicit decoder. You know, of course, if you're on the other side, you flow to the other fixed point, and then you're not correcting anything. You're making the problem worse. I mean, that's true of every decoder. So here's another beautiful family of decoders. It's also, you can also make them fault tolerant. I'm sure probably people will talk about these decoders elsewhere at this conference. But the one that I want to focus on for this talk is a tensor network decoder. And this was first written down by Bravi, Suchara, and Vargo. So here the idea is the tensor network that we define. So what is a tensor network? Each one of these little blocks that has legs around it is a tensor. So this one here labeled S is a 4-index tensor. And in this particular decoder, each of these legs has dimension 2. And as I contract this tensor network, I will eventually get a larger and larger bond dimension until I reach some number chi. The effective vector space dimension gets larger and larger until I reach some dimension called chi, which I'll call the bond dimension. And so what BSV did is they defined specific choices of these local tensors that correspond to the qubits sitting on the horizontal or vertical links and each of the stabilizers. And for an appropriate choice of local tensors, you can prove that the contraction value of this tensor network exactly gives you the probability of each of the logical classes for the maximum likelihood decoder. So this is a way to write down the maximum likelihood decoder. And then this bond dimension that I mentioned is a way to get a tunable approximation of this optimal decoder. So as I crank up chi, the bond dimension, I get a family of decoders parameterized by chi. And the runtime for contracting this tensor network, or at least approximately contracting this tensor network, scales like n the number of qubits times chi cubed. So it's a polynomial time algorithm that gives an approximation, tunable approximation, of the maximum likelihood decoder. So that's why I'm going to use it, because I'm going to be interested in constructing optimal decoders. I should say that there's another method for understanding what the optimal error correction threshold is based on mapping to statistical mechanical models, but that's not really constructive. That just tells you what the optimal value of the threshold is by using Monte Carlo simulations of StatMech models. It doesn't give you a constructive approach to building that specific, to building a specific decoder. This tensor network decoder is constructive. Okay. Thanks. Right, so okay, I mentioned that I was going to show you something about, channel coding, basically. But I want to do it from a very physical perspective. I want to keep these locality constraints. So we tried this just unbelievably simple thing to deal with the biased noise, which was if the dominant noise is Z-biased, so Z-biased noise commutes with all these stabilizers. So on this slide, each of these B operators is all Z. If I have a Z error, it's just going to commute with all these. I've basically thrown away half the bits of syndrome that I might have had, that I might have been able to use to diagnose those errors. And when you tell people initially, well, here's our idea, let's just change half of the stabilizers. Instead of making them Z, we'll make them Y. Well, no, that's not going to work because the bits that you extract are going to be redundant. This is what everybody says when you first tell them this idea. And that turns out to be wrong. So if I flip a bit right here with a Z error, and I have the original one, the original stabilizers, it indeed will only flip these two adjacent vertices. If I change to these Y stabilizers, it will also flip these two adjacent plaquettes. Okay? So for that one specific isolated error, it is indeed redundant. But if I start having chains of these errors, it's no longer redundant. So once I start composing these things, then those bits of information are not redundant because they don't travel along the same lattices even, okay? So that means that in the low error regime, we don't actually expect much difference by making this change. But in the high error regime, we genuinely do have more information about the errors. The question is, can we take advantage of that extra syndrome information and extract it optimally so that we can get an advantage in the error correction threshold? And so that's why we're interested in this BSV, the Bravi-Suchara-Vargo decoder, because it's an approximation of the maximum likelihood decoder. So that lets us constructively build approximations to the optimal decoder. Okay, so those are the two ideas. It's incredibly simple, just doubling the amount of syndrome bits that we get, and can we actually use those bits of information effectively by using an optimal decoder? Those are the only two ideas. And so we posted this paper on the archive like a week or two ago, and if you haven't seen the paper, then you might want to try to extrapolate from this point. So here are the thresholds for the one on the far left is depolarizing. So as I crank up the bias, you might expect, okay, great, we're going to take advantage of more information. You know, maybe the error threshold goes up to something like here. So I don't know what your intuition would have been about this. Everybody that I queried, with one exception, was like, oh yeah, it'll go up by like 3% or something. And so we were shocked when it went up just an absolutely enormous amount. And it basically tracks the hashing bound. So the hashing bound is an achievable rate for ideal quantum error correction. And we know what the hashing bound is for Pauli channels. This is distinct, of course, from the quantum capacity, which is the ultimate limit for transmitting quantum information through a quantum channel. We do not know the quantum capacity for Pauli channels, except we don't even know it for the depolarizing channel. The only channel that we know the quantum capacity of is a dephasing channel, where it's 50%, because it's a classical channel. So for any Pauli channel where at least two of the Pauli probabilities are non-zero, we don't know this quantum capacity, so I can't compare this to the capacity, but I can compare it to this achievable rate, the hashing bound. And over many decades of bias, we actually see that the surface code performs at the hashing bound. So it performs at a sort of, yeah, I don't want to say it's, well, it's, I mean, it's the edge where we at least know by a randomized argument that there exist good error correcting codes, but these are random error correcting codes, right? So they don't have any structure. We don't know how to decode those codes. Here we do just as well using a very concrete code and a very concrete decoder, all of which is polynomial time. So, so over many decades of bias, the surface code just does fantastically. So I'm probably running low on time. So this slide just shows you, this is numerical evidence of an error correction threshold when you're actually below threshold. If I go below the critical value and I see an exponential decay of the logical error rate, that's a very strong indication of threshold behavior. There's an interesting transition. I don't know if this is associated with an actual phase transition, but there's a transition region in this regime of intermediate bias where actually the decoder exhibits poor convergence. So the decoder seems to require very non-local behavior in order to do optimal decoding. And the last thing I'll say is it may actually be the case that if you tune the surface code appropriately, you can actually reach a 50% threshold, which is the, you know, you can never get better than 50% in the infinite bias limit. Although our decoder, we can't run large enough chi to actually show that. If we try to run a larger chi, our decoder just completely fails. We think this is a decoder fail, not a fundamental failure of the code to correct these errors. So it may actually be that the surface code with an optimal decoder performs at the hashing limit or very, very close to the hashing limit for all Pauli channels for all values of bias, which is kind of remarkable. Daniel's telling me that I need to wrap up. So let me just say, let me just thank collaborators on this work. David Long and Eric Huang are undergraduates at Sydney. David Tuckett is a PhD student who's actually here in the audience today. Richard Kung recently moved to Caltech to do a postdoc, and my collaborators at Sydney, Stephen Bartlett and Andrew Doherty. We currently have a postdoc position open if this looks like someplace you might want to live. Maybe you're living in Canada or something. You're a little worried about the winter. you know, or the political stability of whatever nation you happen to live in, then, you know, come on down. Come on down. Apply for our postdoc. And I'll just stop here on the summary and open questions. Thank you.